Getting rid of fossil fuels requires scaling a lot of technology. But what actually are the key technologies we need to scale and develop? Welcome to watch the Sustainable Trends in Business. In this episode, we will talk about hydrogen economy and other keys to the decarbonized world. And we will draw some rabbits out of a hat. Our emissions come mainly from a few sectors: energy, buildings, transport and food. Food is a very complex issue and we will discuss that later, but the other three depend on a few key technologies. Some of these key technologies may solve problems in more than one of the fields, especially energy and transport are quite interconnected. There are a few uncertain technologies that also could become game changers, and we will talk about them towards the end of this episode. The largest problem in the energy sector is energy storage, especially seasonal energy storage. The more and the longer you need to store energy, and especially electricity, the more problematic it becomes. So as this chart shows, only hydrogen and other chemicals provide long-term, long-scale storage. So there is a lot of talk about hydrogen economy, and that's related to this. Some of that talk is misleading because hydrogen economy is not about hydrogen that much. It's a very complex infrastructure, and I hear more and more talk about P2X, and I think it is a much better name for it, despite not saying actually anything. If it was hydrogen, it would actually be a very, very bad idea for Finland. Think of the situation where Finland would have Swedish company building a wind farm, and then that energy from the wind farm going to electrolyzers owned by a German company, going into a German pipeline and then being fed to the Germans. And of course, Chinese will sell the electrolyzers. So what would be the added value? It's difficult to find. So the shift towards P2X, powered to whatever, is important. To understand what it means, we'll have to take a small visit to the chemistry department. And here the basic story starts with actual things that we can get from the nature. It starts from water. The water is fed into an electrolyzer, and then we put some electricity in. Some electrochemical magic happens and we get oxygen and hydrogen out. Well, a few comments about electrolyzers, because they are not as simple as it looks here. Electrolyzers are intended to use cheap energy. So they only make sense if you can use electricity when you have a surplus of it due to renewables, due to solar, due to wind. And then there are two important parameters related to this. Capital expense, so how expensive they are and how adjustable they are. Can they be controlled to respond to that supply? Efficiency actually as a number is not that important. It's not very good. It may be 80% at best, 70%, something like that. But it's not that important, because if you can get a cheap electrolyzer, then it can be much less efficient because you don't have the capital expense. And also, if you think that you would like to take advantage of half of year's hours to have that cheap electricity, then of course the capital expense per hydrogen is double compared to something that uses base load. So that is why CapEx is important. Then adjustability, of course, if you can use the cheap hours of the day, it's a different story from if you need to keep it stable for days and weeks. There are different technologies, and there are some emerging technologies that are quite interesting. For example, proton exchange membrane, PEM, is a promising one and a much researched one. It's evolving quick. And then another note related to electrolyzers. As you know, the electrolyzers produce hydrogen and oxygen out of water. If you find use for pure oxygen, there will most probably be a lot of it available. The need for oxygen currently is much lower than the need for hydrogen. So the traditional idea is to store the hydrogen and then use a reverse reaction in a fuel cell to put hydrogen and oxygen in and get electricity out. That may work somewhere if you have to have that salt cavern to put that hydrogen in, but the availability of hydrogen storage is a geological thing, not for us, not for Finland. And today, and quite for some time, for some decades probably, all the green H2, so all the hydrogen that is produced with renewable electricity will be used in industry. And the need is increasing due to, for example, steel reduction. Hydrogen is also suggested as a fuel even for vehicles. It is, however, a difficult substance to handle. It escapes easily because it's such a small molecule. It is the lightest molecule. It makes metals brittle. It requires special materials. It needs to be stored in high pressures. For example, car pressure storages have 700 bars, 700 atmospheres of pressure in there. And it explodes in a wide range of mixtures with air. So small leakage, big leakage, it will explode. And one thing is, that's quite interesting, but it's difficult to burn in diesel engines. So despite it exploding, it's not a good fuel in engines most of the time. So if we want to do something that has less of a bad temper, then let's capture CO2 from flue gases, so from a smokestack, or air of course. And we use that carbon in a Sabatier reaction to give methane, same as biogas or natural gas. It's a great fuel, it fits current infrastructure, we could use as much as we can get it. It's much easier to store even in large quantities. Well, that's one possibility, or we can take something else out of thin air. Nitrogen is what consists, is 80% of the air we breathe, so there is a lot of it. We take hydrogen and nitrogen, and then we have the Haber-Bosch process. We can bolt these molecules together to give ammonia. Or we can put water and nitrogen directly and then electricity to produce ammonia and oxygen in certain types of reactors. Ammonia is, well, it's smelly, corrosive, toxic, and so on. But it's easy, or relatively easy, to store as a liquid. It doesn't escape as easily, and it can be used as a fuel in diesel engines. For example, Wärtsilä is doing a lot of research on these, on marine and power grid diesel engines. It wouldn't be that good, ammonia, for cars or airplanes though. But there is one other use. It's absolutely essential for us in fertilizers. We would probably die of hunger if we didn't have enough ammonia. Well then, another possibility to combine hydrogen and carbon dioxide is to give methanol, and there are different processes, even some hot co-electrolysis processes where you feed in water and carbon dioxide and electricity and you get methanol out. And this is also something that there is a lot of emerging business on the field. Methanol is a liquid at room temperature. It is again toxic and corrosive. But it's useful as a storage medium. It's easy to store and it can be used as fuel. Plus, it is a very handy building block for any petrochemical products. So, sustainable aviation fuel, plastic polymers, or if everything goes wrong, then you can make ethanol out of it and just be drunk for the rest of your life and stop worrying. Anyway, from this on, standard industrial, chemical and petrochemical processes can be used to produce anything that is produced out of crude oil. Now, future is difficult to predict which one of these will be the main route. Most probably we will have, to some extent, all of them. The processes will win which have the lowest capexes and best adjustability, most likely. But it should be remembered that the adjustability only applies to electricity use. Once you have used electricity, you have something that you can store, and then the next process can be something that's running steadily. And also, the adjustability at the hourly level may not be needed because that can be covered by batteries, possibly. So it's just a little bit more capex than if you have an inflexible process. But you need to have the flexibility in the weekly or monthly basis to be able to answer to the seasonal changes. And this further emphasizes the sort of what I call sugar factory nature. Sugar factories are interesting because the campaign, the time they are running, is about 6 weeks, a year in the autumn. And then they shut them down and they come back 10 months later just to sort of clean them up and start them up again for 6 weeks. And this is the same thing, so the capital expense is very important. How to run something that is used only for a few months, a year. The entire ecosystem will be complex. We talk about disrupting whole chemical and petrochemical industry completely. Then the other big one, apart from energy, is transportation. It's another large sector. There are some things in transportation that are relatively easy to solve and some which are not so. Land transportation can use rails or rubber tires. Of course, rails are great because you can electrify rails, and this is going as far as having battery trains in some places because it's cheaper to have batteries in the train instead of putting the cables overhead if you don't have a lot of traffic on some spur rail. Light road traffic, of course we need to move everything we can to the rails, but rail infrastructure is very expensive. Light road traffic, that is passenger cars and so on, they evoke a lot of emotions because for some reason cars are part of our identity, but there is really no alternative to battery electric vehicles because hydrogen will be too expensive and it has low efficiency. Fuel cells are complicated, there will be a lot of things to maintain. That might be used in some special uses but not in the mainstream. Then we can use biomasses, fuels made out of biomasses or biogas, but they are sorely needed elsewhere. We must not use them for cars because cars can use electricity. And also battery electric vehicles are beneficial from the energy infra point of view. They give demand flexibility, they can take advantage of the arbitrage, thus keeping the price fluctuations down. Then we have the heavier short distance traffic. That is a bit more difficult, but it's going that way for economic reasons. So we are having more and more buses and small lorries and so on running on electricity. And it's also the same grid point of views apply. Heavy long distance traffic is a question. Large trucks for hundreds of kilometers. There the battery cost is high because you need to have megawatt hours of battery, or then you need to have very fast chargers every 200 kilometers. Either way, it's costly. Hydrogen fuel cell might be a viable alternative because the downsides of hydrogen are not that big in a truck because you can carry a huge container of hydrogen with you, so the tank can be huge, and then the cost of the fuel cell is not that big part of the total cost of the truck. Or even e-fuel, that is fuels generated by electricity. They might have better price points. On the other hand, the progress has been fast, it has been surprisingly fast. This is an electric truck with 64 tons of total mass, which is used for daily transport by a whole transport for carrying steel. It has over 600 kilowatt hours of battery in it. The charging network is interesting though, because you need to have megawatt range chargers there. Of course, everything can be as today. We can just sit on our hands with road traffic and just use e-fuels, that is fuels produced from P2X. But then the fuel cost will be 3 to 4-fold compared to today's cost, so it will be very expensive. So, and it's good to remember that the alternative solutions do not need to be today's fossil cost, they need to be less expensive than the e-fuel route, which is 3 to 4 times as expensive as today's fossil cost. Well, that's about land traffic. Then we have marine traffic. Marine traffic cannot go electric. The energy use is too high. There, ammonia and methanol are viable options. Methane is already used, methanol is actually already used, and ammonia is just on the brink of being used, so all three are going to be used. And then there are some other possibilities, such as taking advantage of wind. There are several technologies in pilot phase. Norse power here is one of them. And these are actually much more complex than they look. Aerodynamic wonders, I would say. But these solutions provide typically maybe up to 20% fuel savings. So they are not making them sail ships, but they are providing fuel savings. And this is another take on the same theme, a kite by French Air Seas. So something like sail ship version 2.0. Maersk is betting on methanol, and there is a lot of methanol production in China at the moment. Hydrogen seems to be quite unlikely, no one is talking about it anymore. And it's quite evident why. And then we go to air traffic. That is a tough problem. There have been some ideas of hydrogen planes, for example. Here are Airbus's ideas. A traditional turbojet and turboprop, just using hydrogen instead of jet fuel. Then a blended wing concept, this strange looking thing with huge hydrogen tanks. And plus, of course, a fully electric battery, electric regional propeller airplane. So batteries, or then you can have hydrogen tank and a fuel cell in there. None of these break the laws of physics. All of them are technologically feasible in the sense that if we spend enough money, we will most probably be able to produce any or all of them. But they have their challenges. Hydrogen tanks require a lot of space. And airplane is not exactly where you have a lot of space or can carry massive stuff with you. Well, luckily the energy density of hydrogen per kilogram is better than that of jet fuel, which makes things a bit easier, but of course the tanks are quite heavy because you have high pressure or liquefied hydrogen. So this will require a complete redesign of everything. The airplane body, its wings, the engines, all the tech in the airplane. And what will that cost? That threshold might be prohibitive. To understand the magnitude of what it might cost, designing Airbus 350, which was an incremental design. Yes, a new airplane with a lot of fancy technology, but still looking mostly like the previous ones. That design process cost about 15 billion euros. Designing a new jet-geared turbofan took Pratt & Whitney about $10 billion. Just a new engine, looking like the previous ones, a bit more fuel efficient though. Again, an incremental design. So what would it cost to design everything anew? Anyone's guess, but I would say that $1 trillion, that is million euros, might not be enough. Who is going to pay for that? Not even Airbus or Boeing. Hydrogen would also need very expensive infrastructure on all airports. That's the other side of it. So that also makes it a difficult fuel for aviation. For regional small airplanes carrying like 19 people, batteries are a viable option. There are a lot of startups trying to produce these, and most probably within a few years there will be a couple of alternatives on the market. But the range is limited. It's about a few hundred kilometers, because after that the battery mass will be too high for flying. Interestingly, these are cheaper than current airplanes to fly and operate, and easier and less maintenance and so on. And that may lead to a situation where they actually create new aviation instead of replacing existing. Well, that's an exciting possibility for some very fast public transportation between regional hubs, but not a solution to today's air traffic problems. So at the moment, unfortunately, the only viable option seems to be for the next decade, at least 3-4 decades, seems to be sustainable aviation fuel, SAF. That can be produced either out of biomasses or then P2X, so as an e-fuel. And that use will sip all the P2X, e-fuel or biofuel we can produce for a very long time. And this is the very reason why we shouldn't use biofuels for cars or anything where we can replace them with electricity, because in aviation we can't. And even with this transition, aviation will become much more expensive than it is today, especially long-distance aviation. Personally, I think it's a good thing, but then it has some quite profound economic impacts. Now we have talked about energy and transport. We have buildings. Building emissions can be split into two: building, so constructing the buildings, and then the indoor conditions. According to the World Green Building Council, buildings are responsible for 39% of global energy-related emissions. And this 39% is split so that 11% comes from construction and 28% from use. So more from use than from construction. The picture is largely the same in Europe. The European statistics says that it's around 40% of emissions, so the same, and 2/3 of that coming from building use, HVAC, heating, ventilation, air conditioning. And in there actually mostly heating and ventilation together. So keeping things warm during the cold season in Europe. But let's look at the construction emissions. They are often bound to concrete and steel because we use a lot of steel in forest concrete. In the short term, it is a very good idea to replace these by wood, timber, but of course it's not viable in most cases, so we need to do something about that steel and concrete. Concrete manufacturing process is surprisingly complicated actually. Concrete has been used for over 2000 years. The oldest concrete structures still in use are over 2 millennia old and in good shape. The chemistry of concrete is also very complicated. There is no such thing as concrete. There are hundreds of different types of concrete for different uses. But the common thing is that the concrete uses cement, and the manufacturing process of cement emits a lot of carbon dioxide in two different phases or two different sources. Because when you produce cement, what you do is that you take limestone, which is mined, so it comes from a limestone quarry, and then you crush it and then you heat it by burning something very hot under it, and that very hot is usually gas. You need to have well over 100 degrees, and in that process that limestone breaks into calcium oxide and carbon dioxide. So actually carbon dioxide bound to the limestone is emitted to the atmosphere. That's about half of the emissions, and the other half of the emissions comes from burning that gas to heat the limestone, to break it down. So it's sort of insult and injury in this case. Lime kilns require high heat, and it's difficult to replace with anything. So as long as cement is produced with limestone with a traditional process, this problem is tricky to overcome, other than by sequestration, just by collecting the carbon dioxide and then trying to do something about it after that. But one thing is that you can manufacture concrete without having cement as the binding agent there, and this is an example. Carbonade is a Finnish startup, and they are using, instead of the lime-based cement, they are using industrial ashes or even biomass ashes and carbon dioxide to create the binder for the concrete instead of using cement. And quite surprisingly, the carbon footprint of 200 to 300 kilograms of carbon dioxide per cubic meter of ordinary concrete turns into minus 100 kilograms, from plus 200 to minus 100 kilograms. So actually the process binds carbon dioxide. Carbon dioxide is fed into the process and it is turned into carbonates into the concrete. Well, this sounds too good to be true. Time will tell. There is pilot production going on and it looks good, but we have to remember that 2 millennia of history with concrete, so there is a lot to catch up before these kinds of technologies really become the mainstream. Cost is very important. Cement is very cheap at the moment. So it may be that we need to pay for the emissions of cement before we turn into these better alternatives. And carbonate is not the only one, of course. There are other players in the field, so it's not only one card. And then we have the other challenge, which is steel. And there, iron is a very good material. It has a lot of great properties. It's strong, it's abundant, there is a lot of it in the crust of the earth. It's easy to mine, easy to use, easy to recycle. There is a lot to like about it. It's not very toxic, for example. But steel manufacturing, when you manufacture steel from iron ore, uses carbon to so-called reduce the ore, which means that to take oxygen out of that iron. And there are other chemicals you can use for reduction, and the obvious replacement is hydrogen. So instead of throwing coal into that molten iron, we'll blast pure hydrogen into the iron, and the oxygen happily leaves instead of carbon dioxide, it leaves as water. This sounds great in theory, but of course in practice, if you think that you have molten iron, yellow hot over 1000 centigrades, and then you blow explosive hydrogen into that, there might be some practical difficulties. Not that big though. There are large industrial projects afoot SSAB, a Swedish company, has a very large project which will be ready in 2 years called Hybrid, and this is progressing fast. There are no obvious scaling problems apart from hydrogen availability, but of course once we have large-scale production up, we know much more about the price level. And of course, abandoning fossil fuels in heating and reduction of steel manufacturing increase electricity use, because we have to manufacture that hydrogen somehow. We have to produce that heat by electricity and so on. And this further emphasizes the importance of low carbon electricity, renewables. And it's not a coincidence that SSAB is a Swedish company, because Sweden is one of the few places in the world where this actually can happen. Finland is also one of those places. So concrete and steel constructing the building, they have solutions, we just need to see them scale. Then we have building heating, and that is a multifaceted problem. There is some good news. It is that, at least in principle, we can use low temperature heat with hourly flexibility. We don't need to heat now, we can heat 2 hours from now if we want, because buildings are large energy heat storages. And all sorts of waste heats from industrial processes and data centers and everything are okay, because it's so low temp. But the bad news is that our infrastructure is not built for that. We know how to build new energy efficient buildings, but the problem is here. Existing buildings are difficult and expensive to renovate. It is easy to see a heating future with a lot of heat pumping, solar heat, even local heat storages. It is much more difficult to see how it scales. And I say this as someone who is in the business. This will be a huge problem. Of course, the problem is different in different places. In Finland and Sweden it's sort of easy because we have district heating, so when the district heating decarbonizes, then that's easy, and then we have a lot of clean electricity for heat pumps for those who want to use heat pumps. But for example, in Germany, a lot of gas, even coal, is used for heatings in the buildings, so they actually burn coals even in people's apartments in some cases. How to replace that? Yes, by heat pumps. Air heat pumps are usually air-to-water heat pumps are what is one solution, but the problem with them is that they need a lot of electricity, which they are producing by fossil fuels, with no road to the future. So that will be a much more complicated issue. Well, there are, instead of rebuilding existing buildings, there are some low-hanging fruit to get a bit further. Better control of existing systems like the heat distribution system, heating system, gives 15% of energy savings, and it enables demand response, that is demand flexibility, with very short payback period. That's possible, and that's something that should be done because buildings are usually controlled in a very suboptimal way. And there might be room for another 10 to 15% with some more optimizations regarding ventilation and maybe light renovations on demand renovations. But beyond that, with the existing buildings, hybrid heating systems, yes, possible, but quite complicated things. And as buildings are sort of 100-year investments, this problem will become more pronounced because as we are decarbonizing other sectors, as we are getting the energy consumption for other sectors down, then of course the proportion of buildings becomes more pronounced. And most of private citizens' money is bound to walls. That's another problem. But again, a problem is a flip side of business, so there will be a lot of business trying to solve this. But before we conclude this episode, let's look at some magic. There are a couple of technologies which I call rabbits out of a hat. They're not physically impossible, but they may be game changers one way or another in this game. All of them are researched intensively, so I'm not revealing any secrets. And it's likely that there are no easy wins, but if one of them or a couple of them would break through, then that would be a great help. Our first rabbit is the big one, fusion power. The idea of a fusion reactor is that hydrogen in certain isotopes is fed into a reactor, and then this hydrogen nuclei merge into a helium, another element, and produce a lot of energy in the fusion, as promised by Mr. Einstein. Good news compared to today's nuclear reactors is that the supply of fuel is unlimited. You can get it from the sea if you want, and also it doesn't produce any radioactive waste. The helium coming out of the reactor is not radioactive. The fuel can be so-called heavy water, that is and hydrogen out of heavy water, deuterium, tritium, which is another isotope of hydrogen. It can be lithium in some cases. Well, that's getting a bit more complex, but anyway, it's sort of easy to manufacture, and, at least in theory, not running out. And in theory, everything of course works. However, sustaining a stable energy-producing fusion reaction at 150 million centigrades is not easy. The record is, at the moment, 5 seconds. Well, that's more than 5 milliseconds, but still a long way from something that produces useful energy. Tens of billions have been used since 1960s for the research, and tens of billions or hundreds of billions will be used before we have anything commercially successful. But if we get something successful, which might happen in 2050s, 2060s, it would solve a lot of problems, not leaving radioactive waste, being, very scalable. It's worth pursuing, but I wouldn't rely on it, to be honest. The next rabbit, flow battery. The idea in flow battery is that a battery would consist of the electrodes and then large reservoirs of liquid electrolytes. The energy would be bound to the electrolytes, so the liquids. It's very, very, very scalable. If you want to have a bigger battery, then just add more electrolyte. And as it's liquid, then the energy density is good as well. And you can use it for seasonal storage and so on. So this is something that's simple to think of, and of course the first ideas have been tossed around 150 years ago, but it has turned out to be very difficult to create these. What we have are toxic, expensive, short-lived. But if we can solve these problems and get these cheap enough, of course this would solve many difficult storage problems. First at the wind time scale, but then possibly also in the seasonal storage. A real game changer. Third rabbit. Direct conversion of solar to hydrogen. No electricity, no electrolyzer, no nothing. Cheap hydrogen production for everyone, and everyone in this case includes especially Global South. So if you want to have hydrogen, just put a small factory onto your backyard and then you have hydrogen. Well, of course, having that in all Global South backyards sort of brings us back to the problem of oil, where the oil is not controlled by democratic nations. That might be a problem. But anyway, there is very little progress in the field. It's not so easy in practice. I was slightly participating in a project trying to do this that was in Nevada about 15 years ago. And I must say that the chemicals, for example, used in there were not very nice. They were extremely corrosive and toxic and so on. So this doesn't seem to be an easy one, but theoretically possible. Another rabbit, slightly similar to the previous one, would be a biochemical process using algae or bacteria plus sunlight to produce methane or even methanol. The same arguments as with hydrogen. If you have sun, you have fuel, and in this case you have something even more useful fuel. There are very interesting bacteria around, for example methanotrops. Methanotrops eat methane and excrete methanol, and there are bacteria producing methane and so on. Well, that's, the biogas thing. But making all this easy, cheap and reliable is not easy. Biochemical processes tend to be quite ill-tempered. And then we have the last rabbit, which is a black one. Carbon capture and storage, CCS. The idea is that if we find a good place to stash our carbon dioxide, we can continue emitting it. And we can use old oil and gas fields. They are great. Hey, again, the Norwegians win. And there are plans to do this in the large scale. But of course, For this to be a real solution, the storage should be large, inexpensive and safe for tens of millennia. Not for tens of years, but tens of thousands of years. And up to now, nothing fitting the bill has really cropped up. Of course, there is a huge push from the fossil industry to make this happen because this is their sort of escape route. And it is not impossible, but we will talk more about it later on. I would not count on it anyway. So, after all these magic tricks and rabbits, it's worth noting that for the time being we need to play with the cards we have, not by wishful thinking. We seem to have everything we need. We don't necessarily need completely new technology, but we need to make tough choices, we need to pick something and we need to make decisions. And it will cost a lot. But again, costing a lot creates a lot of business. That's all about energy, I think. Let's talk about something else next time. See you.